Okay, this video will be on the factorisation. Ooh, that's a bad F. Factorisation of polynomials, and we've already done sort of factorisation. We've already done some simpler ones, some quadratic type things. We're going to do some more messy ones, so cubics, and quartics, and things like that. So let's have a look at it. First, you'll remember when from real algebra, sometimes you'll get that sort of situation, and that cannot be factorized anymore. There's no factorization. I don't think there is anyway, but you get to some places where you can't do any factors anymore, and there's a quadratic here of degree 2, and you can't actually factorize it anymore. You get stuck. That does not happen in complex. In complex algebra, if you have a polynomial which has a degree of n, in other words it has z to the power n, then you'll get n linear factors. Okay, so if you've got a z cubed plus whatever, then that can be factorized into three linear factors, z minus 2, z plus I, etc. If you've got a z to the 16 plus 5z to the 7 plus z plus 5 or something like that, then that's a degree 16 polynomial, and so you'll have 16 linear factors. And so a linear will just be z minus some complex number, so I or 2i or z minus 2i plus 4 or something. That's a 5. They're all linear factors. Okay, so that'll reduce down to 16 linear factors. That's the first thing to note. So it can always be factorized. Always. There's no expression in complex algebra that cannot do that. Secondly, is the second thing to know when you're factorizing is the conjugate factor theorem. And very important and very powerful result. And what this says, if, now I'm going to put lots of lines, if the coefficients of a polynomial are real, okay? If the coefficients of a polynomial are real, then the complex factors will appear as conjugates. Okay, so let's go through that again. So if you're looking at some polynomials, so something plus 3z plus 1, if you're looking at that, it's got real coefficients, the number in front of the z's are real, then what you'll find is that it will come out as whatever. What's the conjugate of z plus 2i? It will be z minus 2i. Okay, they'll come out as pairs, and that'll always happen. So anything that's complex will come out as a pair. If you've got a cubic, something like that, you've got a cubic, what will happen? We've got an odd number. If it has any complex solutions, then they will come out as 2. Okay, so there'll be a pair of those complex, and there'll be one left over, and that one must be real. Okay, because you've got these two complex ones, and they're pairs. They come out in 2s, and they'll be complex. And this one has to be real, because if it was complex, it would need to have a pair. They will appear as conjugates, but it doesn't. So that one must be real. So anytime you've got a cubic with real coefficients, you will get 2 conjugate pairs of complex solutions plus 1 real solution. Okay. If you've got a Z4 with real coefficients, then you'll get you could have 2 complex and 2 real. You might have 4 real. There's different situations, but just remember that if you get any complex solutions, then they'll appear as conjugates if the coefficients are real. So really important result that I'll talk to in 1 class. So let's start doing some examples. Let's start to do some factorization. This is possibly the hardest thing in complex numbers, and people hate it, and it's good to get good at these types of things. So let's have a look at it. Let's have a look at z cubed minus z squared minus z plus 10. Let's factorize this guy. Now, first thing to note is it has real coefficients. Therefore, the conjugate theorem comes into play. If there's any complex solutions to this, we're going to get conjugate pairs. And also, it's a cubic, and so you get conjugate pairs, but you also get one real solution. So there's one real solution, one real root, pardon me, because it's not an equation, one real root to this. So let's try and find that real root. Let's try and find this. Now, looking at this 10, it's got to be a factor of 10, whatever this root is. So it's either going to be 1, 2, 5 or 10, okay, and that might be any of these plus or minus. So they're the numbers that we need to search for. Let's call this polynomial PZ. PZ is equal to that, and let's just try a few of these numbers looking at the root theorem, because remember, if Z1 is a root of this equation, then PZ will be equal to 0. That's the factor theorem. So let's have a look at it. Let's just try a few numbers. Let's just try P1. What happens to P1? You get 1 cubed, 1 minus 1 plus 10. That's not equal to 0. Okay, try P negative 1. You get negative 1 minus 1 plus 1 plus, no, there's no way that's not equal to 0. Let's just try 2. P2 is equal to 2 cubed, 8. This probably looks a bit more promising, it's closer to 10. 8 minus 4 minus 2 plus 10. So you get 8 minus 4, 4 minus 2, 2. No, that's not equal to 0. Try negative 2. Negative 2. It's good to start with the lower roots. Generally they tend to be lower numbers, the real roots. Z cubed is negative 8. This could be it. Minus 4 plus 2 plus 10. Negative 8 minus negative 12. Yes, that's equal to 0. Okay. Therefore, negative 2 is a root. And that means that Z plus 2 is a factor. Okay, so understand the difference between roots and factors. Great, so now that we know this, how do we find the other parts? And so let's do this. I'm just going to go to a new screen. Okay, so we've got Z plus 2 being a factor, and what was our polynomial again? PZ was equal to Z cubed minus Z squared minus Z plus 10. Okay, and so far we have found that Z plus 2 is a factor. So what we can do now is just do a long division, and there's a quick way. I'll show you this way for now. I'll probably show you the quick way in class because I don't want to spend too much time here because I can only go for 15 minutes and YouTube doesn't let me go longer than that. Okay, so let's just do this division. Remember your polynomial division. What do we need to times Z by to get Z cubed? We need to times it by Z squared. So let's times all this by Z squared. You get Z cubed. What's 2 times Z squared? Plus 2Z squared. Do a subtraction. This minus this, they cancel that to 0. Negative Z squared minus 2Z squared is negative 3Z squared. We bring down the negative Z. What do we need to multiply this by to get negative 3Z squared? It would be negative 3Z. So let's now multiply that by this, and you get negative 3Z squared minus 6Z. So negative 3 times that. Yep, that's right. And now we'll subtract these. Now we'll get 0 there. Here you've got negative Z plus 6Z, and you get plus 5Z there. Then you bring down the 10 plus 10. What do we need to multiply this by to get this? Will be 5, so plus 5. Multiply that away, you get 5Z plus 10. And good, what you want to get is 0 here. You need this to happen for this to be a perfect factor. So what we have here is this is your other factor. It's a quadratic factor here. Okay, so it's a lot of work. Factorizing is a lot of work. I'll just come over here. And so therefore, at the moment, we have that this polynomial is equal to Z plus 2 Z squared minus 3Z plus 5 so far. Okay, let's finish this off. We can either do completing the square, we can even use quadratic formula if you want. I'll just do completing the square so far. So I'll just do Z squared minus 3Z. What do I need to add here? Negative 3 divided by 2 is 3 over 2 plus 9 over 4 minus 9 over 4 plus 5 equals Z minus 3 over 2 squared. And what's this? That's 20 over 4, so negative 9 plus 20 is plus 11 over 4. Check that. Negative 9 plus 20. Yep, so that's correct, 11 over 4. So that equals z minus 3 over 2. Z minus 3 over 2. And there we'll get the square root of 11 over 2i. I've run out of space a little bit here, sorry. 11 over 2i. And one will be plus and one will be minus. Okay, so that's just, we've just settled that. And so therefore the finished factorisation pz is equal to z plus 2 z minus 3 over 2 plus root 11 over 2i, that's an I there, sorry, and z minus 3 over 2 minus root 11 over 2i. And there's your factorisation. Okay, what I might do, because it's going to be a long-ish video, is I'll stop there. So that's the full factorisation. If it asks for you to factorise, that's what you need to write it as. If it asks for the roots, then you're going to be writing the roots. What just in here, what are the roots? So if it asks for the roots are negative 2. Negative 2 is the first root. The second root will be 3 over 2 minus root 11 over 2i, and the third root will be 3 over 2, sorry about this, plus root 11 over 2i. They're the roots, okay? So please understand the difference between factors and roots. I'm going to leave that there. This will be continued in the next video because I'm going to run out of time.